I have, I have a tentative group for Journal Club where I've basically, it worked out great. I just split you up into the day that you're presenting. So if you were presenting on a Tuesday, then you'll be responsible for the Journal Club discussions on Tuesday, and vice versa for Thursday. And it worked out evenly. So pretty easy. Today, now I wanted to go over the midterm review with you guys. And like I said, I'll post a key to the midterm after this at some point. So without further ado, unless you guys have anything else you'd like to bring up or discuss, we can get started on that. Sound good? Okay. Okay. Let's start by sharing the screen, and okay, so you guys can see the midterm on my screen. All right, so for the first problem, it's we're going to be looking at iron hydroxide, iron 3 hydroxide, and they're asking us to calculate the mass of iron. They're looking for an equilibrium constant and looking for grams. So anybody know what we need to do to start this? I'll give you a clue.
Right at the equation for KSP.
Make an ice table and use KSP.
Yes. Let's kick it. Ice, baby. All right, so we need to make an ice table. And,
Hey, Carl, how long have you been waiting to do that for?
Oh, I mean, forever.
Since the 90s.
Yeah. That was my formative years, man. Vanilla Ice, MC Hammer, the Teenage Mutant Ninja Turtle movies with Vanilla Ice in it. That was me. Although I never had like shaved haircut or anything. Never wore hammer pants, but I never had a rat tail either, and that was also my era. So, FYI, more probably TMI really. But all right, so with this, we got to know the equilibrium equation, right? So essentially, we're having iron 3 hydroxide, and that's a solid. Okay, can you guys see this?
If I pin you, I can see it.
Okay, what does that mean?
You can like go to the top corner and pin a person.
Yeah, because
so I
it's
just
not
pin you.
Wait.
It's not the center video right now. It's the ICA midterm review.
Let me stop sharing.
There we go.
Okay. And does that turn out okay? Is there like glare or anything? Can you see it?
Yeah.
There's a little bit of glare, but it's completely, you can definitely see the problem.
Okay, great. That's what I'm looking for. It's workable. Okay, so this is going to dissolve. So what happens when it dissolves? It dissolves into iron 3 and OH, and then these are going to be aqueous. And we got to balance it, of course. So that's looking good. And so now we can do our ice table, right? So now what are we given? Well, we're not given anything. So starting initially, we have 0 for our concentration. And the iron 3 hydroxide is a solid, so it's not going to be a factor in this equilibrium. And then the change is going to be plus X. And the change for the hydroxide is going to be plus 3X, right? Because of that 3 coefficient there. And then what are we given? We are given the KSP. So from that, we can say that this is going to be just x and 3x. And so we can say that the KSP that they give us, which is 4.0 times 10 to the negative 38, 0 times 10 to the negative 38 is equal to the products over the reactants, or in this case, just the products, right? So it's going to be x times 3x, but then we got to cube it, right? Because of that 3 coefficient up there, okay? Now, if we crunch that together, right, 3 cubed is 27, and x cubed is x to the third, times another x, so we can just write that as 27x to the fourth is equal to 4.0 times 10 to the negative 38, okay? And then you would solve for x, right? By dividing each side by 27 and then taking the fourth root of that. And if you do that, what you should get for x is 2.0 times 10 to the negative 10 equals x. Okay. Now they want to know for this first part, what is the mass of iron 3 hydroxide? Okay. So if this is x, we can basically say that that is the concentration. It's the concentration of iron, but it's a 1-to-1 relationship, right? Iron has a coefficient of 1 and iron 3 hydroxide has a coefficient of 1. So we can use that same concentration for the iron hydroxide. And if we do that, we can say that 2.0 times 10 to the negative 10 moles per liter, we just go to grams, just stoichiometry, right? So we multiply by the molecular weight of iron, which happens to be, is it iron or iron hydroxide?
It's the iron hydroxide.
Hydroxide. And what's the molecular weight of that? Did we get that?
159.69 grams per mole.
Grams per mole. Okay. And so if you can calculate that out, you should get, what is that?
3.13 times 10 to the power of negative 8.
Negative 8 grams per liter. Okay. Any questions there? Make sense? Okay. So that's
So I just want to ask something real quick.
sure.
That's a pretty small number. Does that seem reasonable, just logically, given the KSP that's that small too?
Yeah, so that's a good question. I always like you guys to think about, does that make sense, right? Yeah, I mean, if you think about how much a gram is, and if you think about the solute, because so if that KSP is so low, what does that mean? Does that mean it has a high solubility or a low solubility?
It's low, right?
Solubility, yeah.
So if you're given a really low solubility, you're not going to have a whole lot of dissolved mass. So the grams should be pretty low. And a gram of something is quite a bit when we're talking about these kinds of reactions and equilibrium problems.
I was mainly surprised because I thought that hydroxide compounds were usually soluble in water.
Hydroxides are. The iron, though, is not as soluble. So it just depends on because of this formation, you decrease the solubility because the iron is attached to it. If it was just hydroxide, then it'd be a different story. Okay.
I think I got a different number for the FeOH3. I don't know if I did it wrong or not.
Okay. For the molecular weight?
Yeah, I got 106.8657. I don't know if what everyone else got.
Yeah, I got that too.
Okay.
And then it would make the X calculation 2.10 times.
Yeah, no, I just looked it up. I was wrong.
Well, great. Not great that you were wrong, but great that we are correcting as we go. So 106.867.
57, but yeah. 8657. Sorry.
8657. Okay.
Yeah.
And then that gives you a what, like a 2.1 times 10 to the negative 8. Okay. Cool. All right. So that's A. What's B asking for? In a solution of ethylene diamine tetraacetic acid, or EDTA. EDTA is used in all kinds of different applications, from cosmetics to agriculture. We use it a lot in molecular cell labs and biochemistry labs as kind of a buffer, if you will, not a pH buffer, but what it does is it binds to certain metals, like it's doing in this problem here, that could assist in degrading DNA and protein and stuff like that. So if you're wanting to do molecular biology or biochemistry and you want to preserve your nucleic acid and your proteins, you put it in an EDTA, which will kind of sop up any free metallic ions that might be present. And that's what it's doing here. So in this problem, they're using it to form a complex ion with iron. And oftentimes this is done in agriculture because plants need iron. And because iron doesn't readily dissolve in water, at a neutral pH, it can form this complex ion and become very bioavailable to the plants. So just like an aside note there, but they're saying that it has a formation constant of 1.7 times 10 to the 24. What is the equilibrium constant for the solvation of solid iron 3 hydroxide in solution of EDTA? This one is actually a pretty straightforward problem if you know one simple property. First of all, let's just write out what's happening, okay? So we have iron 3 hydroxide, okay? And that is going to form with EDTA, and that is what, 4 negative aqueous. And that's going to yield this complex ion of FeEDTA plus 3 hydroxides. Yeah, it's kind of legible. essentially you have the iron, which is +3, and the EDTA, which is a -4. And when they come together, what's the resulting overall charge? It's going to be a -1. But to do this problem, all we need to know is that K, which is what they're asking for, right? Yeah, what's the equilibrium constant? K is the product of KSP, or the solubility product, times the product of formation constant, so KF. And that's it. So they gave us, what did they give us? They gave us the KF, so 1.7 times 10 to the 24th. And we have the KSP from the very beginning of the problem, right? It says iron 3 hydroxide is measured to have a KSP of 4.0 times 10 to the -38. 0 times 10 to the -38. So you just multiply those two together, and your K should be 6.8 times 10 to the -14. And that's the answer. So even though B has the most text to it compared to A and C, it's the simplest and shortest of the answers to solve. So don't be intimidated by the length of a question. Okay. The last one, if a solution of EDTA has a concentration of 2.0 molar, how many grams of iron 3 hydroxide can dissolve in 1 liter? Okay. So here we're given a concentration and we're asked to go to grams. So that's going to be our ice baby again, right? So I've already written the reaction up here. Maybe I'll just write it again so that it's all on one line here. So we need iron 3 hydroxide. And I'm going to leave out the property or the phase states just to fit this all on here. Plus EDTA gives us iron EDTA plus 3 hydroxide. Okay. All right. So ice. What do we have? We have the 2.0 molar for EDTA. And what we want to know, we don't have this yet. The change is going to be minus X plus X, and again, plus 3X because of the 3 coefficient in front of that hydroxide. And so, and then of course the iron 3 hydroxide, we don't worry about that because that is a solid. So that's not going to play in our equilibrium. So we get 2.0 minus X, X, and 3X. Okay. We have our K. We just solved it in B, right? We said that the K was equal to 6.8 times 10 to the -14. 6.8 times 10 to the -14 equals X times 3X divided by
3x cubed, right?
3X cubed, thank you, divided by 2.0 minus X. Right? Okay. Now, 6.8 times 10 to the -14. That's a really tiny number, right? So what can we do when the K is a really tiny number?
Assume x is 0 and the 2 minus x.
Yeah, we have our small x assumption. So any time x is added or subtracted from something, we can assume that it's going to be negligible. And so we can remove it from this equilibrium expression, right? So let's just get rid of that. And then we end up with, again, 27x to the fourth divided by 2. And you multiply both sides by 2, you divide by 27, you take the fourth root of each side, and that gave me 2.7 times 10 to the negative fourth m. Okay. Anybody get something different? Okay. And now we can validate this, right? To make sure that that assumption was valid, we can take this number that we get for x, divide it by 2, multiply by 100, and if it's less than 5%, that was valid, okay? Well, let's do that really quickly. So,
Definitely is.
yeah. 4 divided by 2 times 100, and that's 1.35%. So we're good on that. That is our concentration. What are they asking for? They're asking for grams. So same thing we did in A, right? This is moles per liter, so we multiply it by 106 point, what do you say, 8657 grams per liter.
Yeah.
Okay. And 2.9 times 10 to the negative 2 grams per liter. Sound right? Okay. So that's it for equilibrium. We can now put that behind us. Maybe. It might pop up again on the final, but who knows? Well, then you have to do another equilibrium problem on your actual exam too. But for the rest of this test, we're going to get into more of the new stuff, okay? So let's go share the screen. That brings us to our second problem. Balancing these reactions. So what do we have to do? We have to break them up into their half reactions. We should figure out what's being oxidized, what's being reduced, and go from there, right? Okay, so this one, looks like there's a typo there. It should be solid aluminum plus aqueous copper ions, and then that H, it must have been like a formatting thing. Should be goes to aluminum ions and copper solid. All right, so let me write that up here. Al solid plus Cu2 aqueous goes to Al3 plus Cu solid. All right. So let's figure out what's oxidized, what's reduced. Here we have aluminum with no charge going to aluminum with a +3. So that means it must have lost electrons, right? And if it loses electrons, Leo says Gur. Leo, loss of electrons, oxidation. Copper went from a +2 to neutral, right? So that means it must have gained electrons to bring that positive charge down. GER, Leo says GER, gain of electrons, reduction. Okay, so we've got that figured out. Now let's write these half reactions, right? So we have aluminum solid going, I should give myself some space here. We have aluminum solid going to aluminum 3+. What's the first thing we do? We balance the elements here. They're already balanced. So now we balance the charge. We have +3 here. To get that to be neutral, so it's balanced on this side, we just add 3 electrons. Okay. Cu 2+ aqueous goes to Cu solid. They're balanced, so it's good. But we got to balance this, right? And so in order to do that, it's +2. To bring that down, we add 2 electrons on this side. Right? Okay. Next, we need to get these electrons balanced. Okay, we balanced the charge on either side. Now we got to balance the electrons between these 2 half reactions. And to do that, you say, well, what number do these have in common? 3 and 2 both have 6 in common. So we're going to multiply everything in that first reaction. Everything here is going to be times 2 to give us 6 electrons. And everything in this reaction, we're going to multiply by 3. Yeah. To give us 6 electrons. Right? And so if we do that, we should get 2 aluminum goes to 2 aluminum ions plus 6 electrons. And 6 electrons plus 3 copper ions goes to 3 copper solid. Right? Okay. And then we put those half reactions back together. So let me erase, let's go erase this stuff in the middle. There it is. Okay. So we just write everything that's on the left side, put it together, put everything on the right side together, and we get 2, that's hard to see. That's the one that Theo was going to town on. So we'll just leave red out. We get 2Al. The electrons cancel. 6 electrons on each side cancel. We get 2Al plus 3Cu gives us 2Al3 plus 3Cu. Okay. That's it. We did it. Now, we're doing time. We're doing good. Number 3 is pretty much the same process, only because it's basic, and we end up having to balance. I'll go over that. Well, I think we should do that one. I'm not going to skip over that one. All right, so the next one is asking to balance when performed in a basic solution. And so it's this iodine ion and then permanganate giving aqueous iodine and manganese oxide. All right, so we'll write that out. I minus plus MnO4 minus goes to I2 plus MnO2. And that's going to be solid. Okay. Now, yeah, okay. What's oxidized and what's reduced? Well,
Is that iodine oxidized?
Manganese is being reduced.
yes, so you're both right. Yeah. So if we look at iodine, it's going from a negative to no charge. Okay. So it must have lost electrons to lose that negative charge. And so therefore it's going to be oxidized. The permanganate has a negative charge also that goes to a neutral charge. So that might be a little bit confusing, but what you have to look at is not the whole molecule itself, but the manganese. What's going on with the manganese? Okay. So here, what's the charge of manganese?
+2.
No.
Oh, 4.
It's 7. It goes from 7 to 4.
Yeah, so you're right. +2 normally on its own as an element, but in this case, it's bound with 4 oxygens, right? And what's the charge of oxygen? Oxygen,
-2.
yeah, is a -2, and there are 4 of them. So times 4, -8. So in order for there to be a cumulative charge of -1, the manganese must be a +7, right? Because that would give us a difference of -1, and that's why that's there. Okay, so manganese in this permanganate is 7. With this one over here, we have O2. So that's going to be oxygen equals -2 times 2 equals -4. And there's no charge. So that means manganese must be +4 to balance it out. And so what's happened is we've gone from a +7 to a +4. So it's gained electrons. So it's reduced. Okay. And I mean, really, you don't need to know what's oxidized and reduced per se to just balance these, but it's good to be in that groove to understand it and just, you know, be able to exercise that ability. All right. So what do we have? We have our half reactions. Iodine goes to I2. And then we have permanganate goes to manganese oxide. first thing we need to balance the elements. So this is I2. This is just I. So we need to put a 2 there. Here, manganese is balanced, but oxygen is not. Remember, we balance all the other elements besides hydrogen and oxygen first, and then we come back and balance those. Do you guys remember how to balance oxygen?
Add hydrogen to one side and then add hydroxide to the other. Water to the other side.
Yes, water.
Yeah.
Yeah.
It's water and it's hydroxide or hydrogen, depending on if it's an acidic or basic solution.
Yeah. So we have 4 oxygens here. To get another 2 over here, we can add 2H2O. Now we have 2 oxygens plus 2 oxygens equals 4 oxygens. But to create that balance, we've created an imbalance in the protons, in the hydrogen ions, right? We have 4 hydrogen here, which is looking kind of, is that kind of washed out?
You can see it still.
All right, not much I can do, but this is 2H2O. So let's add 4 hydrogens here. Okay. Now the hydrogens are balanced and the oxygens are balanced, but now we've added hydrogen ion, we've added, you know, these protons, and now it's acidic, right? That's the definition of doing this. And so we need to neutralize that. How do we neutralize 4 hydrogens?
4 hydroxides.
Yeah. So we need to add 4 hydroxide to this side. And if we do it to this side, we got to do it to the other side. Okay. Sorry about that, guys. I wish it wasn't so bright. So now that will end up turning this, the 4 hydrogens and the 4 hydroxides, into 4 water molecules. And that neutralizes this solution, right? And we're good at that on that step. What else do we need to do? We've balanced the elements. We've neutralized it. We need to figure out electrons, right? So going back to our first half reaction, we have 2 iodine minus. So that overall charge is going to be a -2, right? So then to this side, we need to add 2 electrons. So now that charge is balanced, okay? Over here, we have a -1. And over here, we have 4 hydroxides, which have a -1 charge. So this is going to be a total of -4. So in order to balance it, we need this to be -4 also. So to get this to be -4, we add 3 electrons. Because 3 electrons plus this 1 negative charge on permanganate gives us a cumulative charge of -4. So -4, -4, it's balanced. Okay? All right. Next thing we got to do, we got to balance the electrons, right? So here we have 2 electrons. Down here we have 3 electrons. So just like we did in that first problem, we got to multiply everything here by 3. and we multiply everything over here by 2. I'm gonna erase this now if that's okay. When we multiply the first reaction by 2, we end up with an overall equation of 6i minus gives us, oh, wait, no. The first one was what? 3. First one was 3. 6i minus, and then 3i2 plus 6 electrons. And then the second one we'd multiplied by 2. So that gives us 8 H2O plus 2 permanganate yields and 6 electrons. Yields 2 MnO2 plus 4 H2O plus 8 OHs. Okay, everybody with me on that? All right.
Carl,
Yeah.
so for the first I right there, would that be 3I, or did I miss that? Did that get doubled somewhere and I missed it?
It got doubled at the beginning because the half reaction is I minus yields I2. And so to balance that iodine on both sides, we put a 2 coefficient on it.
Okay.
So that we have 2 I's on this, and then it's I2. So even though it's a subscript, not a coefficient, it means there are 2 iodine.
Thank you.
Yep. So now all we have to do really is just condense some of the things and then squash it together, right? So what cancels? Our 6 electrons cancel. And we have 4 waters on this side and 8 waters on this side. So we can divide each side by 4 waters. And that's going to cancel out the 4 on this side. And it's going to reduce the 8 here down to 4. And so then all we need to do is write the stuff on the left side of the arrow and combine it with the stuff on the right side. And we have our equation. So 6i plus 4H2O plus 2MnO4 yields 3I2 plus 2MnO2 plus 8OH. And that's it. All done. All right, so here, same thing. We got to break it down into half reactions. We've got to figure out what's oxidized and reduced, but we're taking it a step further. We need to then identify the oxidizing and reducing agents, which are basically just, if it's oxidized, it's going to be a reducing agent. If it's reduced, it's going to be an oxidizing reagent. And then identify the number of electrons transferred. That's when we balance the electrons. And then calculate the standard cell potential, which is taking those values, the EMF values for the 2 half reactions and subtracting them from each other. We got to know what's the cathode and the anode, or what's reduced and what's oxidized to figure that out. And then calculate cell potential with the initial concentrations that they give us. And from that, based on whatever that value is, we can determine if it's spontaneous or not at that given temperature. Okay. So let's see, what do we have? We have mercury. And again, I'm going to leave out the phases, just they're written there. You know what they are. Plus sulfur gives us, oh, no, plus silver gives us 2 silver and mercury sulfide. Okay. This is a little bit more tricky just because we have 3 reactants in there, right? But essentially, we can break those half reactions into silver, and then we can lump these together and say that those are going to there, right? Now we got to figure out what's reduced and what's oxidized. Well, silver has a positive charge on the left side and then has no charge on the right side. So it must have gained an electron to bring it down from being a positive, right? It balances it out to 0. So if it gains it, it's reduced. And therefore, the silver is the oxidizing agent. Sulfur here has a -2 charge. Sulfur over here has no charge. So it must have lost electrons to lose that negative charge. And therefore, it's oxidized. And these must be the reducing agents. All right. Okay. So that's A. For B, to identify the number of electrons transferred, we just write these half reactions out. So it's 2Ag plus goes to 2Ag. Okay. There are 2 Ags with a plus charge. So that's overall a 2+ charge. So how can we get it to where it's balanced so it has the same net charge as this side? We just add 2 electrons. Okay, 2 electrons plus 2 positive charge ions gives you a net of 0, and so that's balanced. For the other one, we have Hg plus sulfur gives us HgS. Okay, charge here is -2. So in order to balance it on this side, we just add 2 electrons. Okay, so now it's -2 on this side, -2 on this side, 0 on this side, 0 on this side. And that's our answer. For B, how many electrons are transferred? 2. We're also going to use that for moles of electrons later on. Okay, so B is 2 electrons. Now they want us to calculate the standard cell potential, and they have given us the values. Okay, so for silver it's 0.7996, and for the mercury to mercury sulfide it's -0.692. So what do we do there, guys?
We would do the cathode minus the anode. So
Yeah.
the reduced, no, is it the oxidized minus the?
No.
The reduced minus the oxidized.
Yeah. The reduced minus the oxidized, AKA the cathode minus the anode. Okay, so what did we say was reduced?
The silver.
Silver. Okay, and silver value is written as 0.7996 volts minus the oxidized value, which is a negative 0.692.
Carl, I have a question about the silver.
Yeah.
Because it says E and then it's AG/AG plus. So since we're going like the opposite way, would it be a negative 0.7996? Or is it still the same no matter what?
Oh, no, that's a good question. I think maybe that's just, I don't know, if we look up that value, is it going that direction? I might have put the plus on the wrong side.
I can look.
Let me see.
I just wasn't sure if that mattered or not.
Yeah, it does, because remember, if we're going the opposite direction, we change the sign. So maybe it's possible. Anything is possible. I could have mixed.
In the book, it says Ag plus the electron goes to Ag is a positive 0.7996.
Plus going to AG is a positive.
Yeah.
Okay.
Yes.
So I think I just must have put the. I
Okay.
think I must have just put the positive. I
On
mean,
the
I
opposite side.
put charge on the wrong side.
Okay.
Thank you. Thank you. Let me change that actually. Oops. Okay. So if we subtract those two, what did we get for that? It's actually this plus that, and so what's that going to be? Our E cell. I got 1.5 volts. Okay. That number we'll use later, all right? Because now they want us to calculate the cell potential with these given concentrations, okay? And if you remember, to do that, we use the equation E cell equals standard E cell minus RT over NF natural log Q. The Q, right? Remember Q? Q is where we put in the concentrations, right? Now, R is our constant, 8.314. T is our temperature, room temperature, so in Kelvin, 298.15. F is Faraday's constant. And remember I said that we typically convert this to log of Q. And when you do that, when you convert log Q, it becomes 2.303 log of Q. All right. Now, 2 is there. Wow. For all of this, we can all, if the temperature, if it's all standard, we can just say that R times T times 2.303 divided by Faraday's constant is equal to 0.0592, right? So we can just automatically put that number in there so we don't have to compute that out every single time we do problems like this. So it's going to be, the E cell is going to be equal to our standard E cell, which we just calculated, 1.5 volts minus 0.0592 divided by N. N is our moles of electrons, and we said that that was 2, which I erased, but it's 2 times the log of our concentrations. They gave us the concentration of sulfur and the concentration of silver. What is it? It's products over reactants. Our products, I didn't write it out, but these, if you look at that equation, are both solids. So they don't have an effect on Q. We just designate it as 1. So it's going to be products 1 over the concentrations of sulfur, which is, what did it say that was, 0.1, times silver, which is 0.25. But remember, we got to put it to the second power. Why do we put it to the second power?
Because of the
Because there's
coefficient.
Yeah. Because there's that coefficient there. Okay. And if you take all of that, 1.5 minus 0.0592 divided by 2 times the log of 1 over 0.1 times 0.25 squared, what I got was 1.43 volts. Okay. Now, spontaneous at 298.15. We did all this calculation under the assumption that the temperature was at 298.15. Okay, so we don't have to do anything else. We can say that this is that value at that temperature. If it was, you know, is this reaction spontaneous at 200 degrees Kelvin? Then you'd have to rework things. But we can just use this value and say, would that be spontaneous? Anybody know if that's spontaneous or not?
Positive spontaneous, I think, right?
Correct, Jacob. Positive or greater than 0, all right, is spontaneous, because remember, these things go from negative to positive, or in some cases, more negative to less negative. All right. So yes, this would be spontaneous. This would happen. It wouldn't need outside intervention to occur. Okay. Next, use the table below to find out rate law, rate constant, what reaction order they are, the overall reaction, etc. All right. First step, let's figure out, in order to proceed with rate law and then from there rate constant, you got to know the reaction order first. Okay, so we have to know the reaction order before we can write the rate law, because the rate law is going to have those coefficients, are going to be raised to the certain powers, 1, 0, or 2, depending on the order that they are. And then once we have that rate law, we can use that to solve the rate constant. So the first thing we have to do is the reaction order. And to do that, we have to, well, actually, let me go back. We have to compare the values, the concentrations of these reactants, and look at from one reaction to the next, we have to see how it changes on one reactant when the other reactant stays constant, and see what happens to the initial rate as a result. Okay. So to do that, we look at let's look at the first two reactions. Okay, we have NO going from 0. Annotate. We have NO going from 0.001 to 0.003. And perfect. H2 stays constant. So we can see what that direct effect of NO is on the initial rate. Okay, right here. So if you take 0.003 divided by 0.001, you should get 3. And if you take 2.8 times -4 divided by 3.1 times -5, you should get 9. So something's changing. What is the order? The order in that relationship from 3 to 9 is second order. Okay? Now, if that doesn't make sense, you can also write it out. We could say that the rate of one thing over the rate of another thing is equal to K times the concentrations.
Isn't it rate 2 over rate 1? Because we did 0.3 to 0.1.
Yeah, I mean, really, it doesn't, in this case, you definitely have to have the second reaction over the first reaction. Yes. I was just designating them as, it's not like K1 and K2. I'm just saying that that's just one of the rates that we're using. That's another rate. So yeah, we can write it as 2 over 1. That works. Okay. But what you want is to have the 2.8, because we're taking 2.8 divided by 3.1 to get that 9 number, right? So we put that on top. So let's say, what was that? 2.8 times 10 to the -5 over 3.1.
I think it's to the -4.
There you go. 4 times 3.1 times 10 to the -5. And what are the corresponding concentrations for that? So for this top one, we have, so this is going to be reaction 1. This is going to be 0.001 and 0.006 over 0.003 and 0.006. Yeah.
Did the opposite since we did 1 over 2? No? Okay. We flipped.
Switched. So this is data from the second reaction, data from the first reaction, and then we switch it to be data from the first reaction over data from the second reaction. And the K's cancel, and the 0.006 cancels, and you get, we have our coefficients M here, and what we can say is that it is, I got 9 equals 0.33 replicand to the M. Okay, and so to figure out what M is, you can take the natural log of 9 is equal to the natural log of 0.03, 0.333. And that's going to be, then you divide each side by the natural log of 0.33. And if you do all that, you get like 1.998 equals M, or 2, right? So we can say that NO is second order because M equals 2. Then if we go on to H2, when it changes down here, it's going from, in reactions 3 and 4, it's going from 0.001 to 0.002. So it's doubling, and the NO is staying this constant. And what's happening with the initial rate? That's also doubling. Okay, so H2 doubles, initial rate doubles. That's a 1-to-1. So it's a first order reaction. So overall reaction is just adding those together. So a second order plus a first order equals a third order. And now we can go from there to writing out our rate law. Okay. We say that the rate law, or I mean the rate, is equal to concentrations to some power, right? What did we say the NO was? We said it was a second order, so we put that to the 2. H2 is a first order, so we just leave it blank, or if you want to write a 1, you can. And that's the rate law. And so then to find the rate constant, we plug in the concentrations that we have in that table. We just pick one reaction. We plug in the rate and the concentrations. And oh, I forgot a K here. Sorry. That's the rate law. K times the concentrations. So to find that, right, that is the rate constant. We just say K is equal to the rate divided by some concentration of nitric oxide squared over hydrogen gas. Okay. So if we just pick the first reaction, what is the rate? 3.1 times 10 to the -5. And then we have 0.001 and we have 0.006. And so we just take this, divided by that squared, and divided by that, and that should give us our K. And what I got was 5.16 times 10 to the third. Now, with units, right, this is here, right, because it's molar. These are the concentrations. So what this is going to end up being is S to the -1 and M to the -2. And why is that? That's because we have essentially M squared and times another M. So M cubed and an M on the numerator. So that brings it down to M to the -2. And it's molar per second, so -1. And that is that's our rate constant. And it should work if you plug in the same values for any of those reactions. I just picked the first one, but in theory, it should work for the other ones too. Okay, now we have this generic reaction, A goes to B, and we have some data. And
Hey, Carl.
yeah,
Hey, sorry to interrupt.
no, that's what this is about.
I forgot where I had seen it for determining the order,
Uh-huh.
and it said that you can do it based on the coefficient, but in this case, we have H2 with a coefficient of 2, but it's a first order. Should I just completely disregard that then?
Yeah, I wouldn't look at the coefficients.
Okay.
You gotta really see what they're doing as you go and look at the reactions and compare them that way.
Gotcha.
So just take that procedure that we just did and see if when one side is constant and the other side, if it doubles and the rate doubles, then it's one. You know, if one doubles and one quadruples, then it's a second order.
Okay, got it.
If one changes and the rate stays the same, then it's a zero order, right? Meaning when that concentration of that molecule changes, it has no effect on the rate, so it's a zero order. So it doesn't matter.
Okay, yeah, I forgot where I saw it. I'll just
Yeah, scratch that.
ignore that.
Wipe
Cool.
that out.
Cool, thanks.
Yep. Okay, so here they say, what is the order of the reaction? And then they give us a concentration. I want to know what the half-life is. And then how much of the reactant is left after 5 minutes. Well, let's look at these. Here, we're plotting concentration of A versus time. So do you guys know, is that a zero, first, or second order?
It would be zero order if it was a straight line.
Yeah. So before we even look at the line, let's just see how they're plotting it. And you're right, Cody. So it's just the concentration of A. So that's zero order. The second graph is the natural log of A versus time. So that would be first order. And then 1 over the concentration of A is a second order. So it's zero, first, second order in that order. And then what we want to do is we want to look at what is the best, right? So clearly 1 over A seems to be the best line, right? And you can kind of see that by just eyeing it up. But if they're close, sometimes they'll be closer than this and it'll be harder to tell. Then the next best, well, the best thing you can do is look at this R squared value, okay? So what's the R squared value of this? It's 0.998. It's pretty close to 1, which is to say it's better than 0.96 and better than 0.85, okay? So it's really just right on the money, and we will say it's a second order reaction. So that's A for this problem. What is the order? Second order. And that's also going to tell us what integrated rate law we use for the rest of the problems, right? Because second order is going to have a different integrated rate law than zero and first order. So the second problem is assuming that the initial concentration is 1.1 molar. What is the half-life of the reaction? Okay. And to do that, we need to know what the integrated rate law is. We have 1 over concentration of A, right? Because it's second order, so we're going to use that one, equals KT plus 1 over concentration of A0. That's the rate law we use. But now we want to know half-life, okay? So we got to just finagle this a little bit. And we'll say that 1 over the half-life, so half of that concentration of A, and it said that that concentration was 1.10 equals K. Did they give us K? They did. How do we know what K is?
Isn't it the slope?
Yes. So if we look here, the slope is 5.22 times 10 to the negative 1. Okay. And in this case, since it's second order, slope is equal to K, right? So we can say that this is equal to K, which is 5 point, what did I say that was? What is it?
2
U2
times 10 to the negative 1.
Okay. 5.22 times 10 to the negative 1 T plus 1 over 1.10. And then we just solve for T, okay? And I got concentration of A. No, we're solving for T. The half-life of T equals 1.74 minutes. Okay. Great. See some thumbs up there. If you got this, but you didn't get this, then perhaps it's just a question of algebra, right? And not doing something quite the right way. So make sure you can take all of this and get this out of that, okay? Which could be trivial for some, could be less than trivial for others, just depending on how comfortable you are with that, okay? So that's half-life. And then they're saying how much of the reactant is left after 5 minutes, okay? So to do that, we would say, what is this concentration when T equals 5? Okay. So 5.22 times 10 to the negative 1 times 5 plus 1 over 1.1 is equal to 1 over the concentration of A. And you have to multiply both sides by the concentration of A, divide by 5.22 times 10 to the negative 1, divide by 5, multiply by 1 over 1.1, and that should give you a concentration of 0.28. And if you wanted to double check
I
that,
got 0.1.
you got 0.14.
0.150, but I was struggling with that step, so I probably did it wrong.
Anybody else get 0.28?
I did.
Okay. Like I said, this morning, I could be wrong, right? I didn't say that specifically, but I said that, authors of textbooks are wrong sometimes. Scientists, when they publish papers, are wrong. Instructors, I'm the best example. I'm wrong all the time. So take it for what it's worth. I got 0.28, so I think that's right. But try it again, Cody, and see if you can get that answer somehow. Okay. And, honestly, for the exam, you guys, most of you should know by now how I grade. If you get this, but this answer is 0.15 something, I'm not going to ding you that much, right? I want to know that this isn't I mean, there's a lot of math in this class, but this isn't a math class, as absurd as that kind of sounds. I'm not grading you on algebra. I'm grading you on, do you understand the concepts, right? So I'm much more, if you wrote, so like we know with homework and stuff where there are wrong answers in the back of the book, if you write a wrong answer and then you garble all this other stuff to make it fit that, I'm going to take off a lot more points than if you do the right thing and the answer is wrong. So just keep that in the back of your mind.
Hey, Carl, I think I missed, maybe you went over this before I hopped on, but we're getting the midterm win, or do we already have it?
It's up now.
Yeah, it was just posted.
Okay.
And it's due by next week, correct?
Yeah, it's due a week from today. So
Okay.
I think that should be more than enough time. Let me know how it's going. If you feel like, if you feel like that's not enough time, then we can reconsider. But I think that should be, especially
And then,
it
sorry,
should
also,
be similar to this.
yeah.
You guys
it's
got
similar.
it in a couple days. So
Okay. Also, I saw that you made like a journal club assignment.
yes.
What is that? I didn't see any like document on it. I just saw.
So next Tuesday, we're having Ian present his paper. And so the Journal Club 2 assignment is just your critique of that paper. Like,
Oh, I didn't see the paper on there. So are we just critiquing his presentation?
yeah. So if you go to, hold on, let me find it.
Find it. Will you screen share?
Yeah, I'm gonna screen share in just a sec here. Let me get to the right page. There we go. Okay. If you go to Journal Club, can you guys see my my canvas? Yeah, okay. If you go to Journal Club, there are the guidelines for how to do Journal Club, and then there are Journal Club papers, okay? So in here, we have JCO1. That was me. And then now we have JCO2. And that's Ian's paper, okay? Now I'm also gonna send out today, is this it? Yes, I've broken you guys up into 2 groups. Per this morning's conversation, we've decided to have you guys just do half the journal clubs. Or you can attend all of the journal clubs, but you're only responsible for half of the papers so that you don't have to read so many papers a week. So for Ian, he's going to be on Tuesday, this coming Tuesday, and Elke, you are in the Tuesday group, okay? So you will read his paper, and the assignment is the write-up, the critique. And I'm going to try to grade the critiques that you gave me for my paper so that you kind of have an idea beforehand what I'm looking for.
Okay, and are we gonna have a lab on Tuesday, or I'm just trying to think what I should do first, the midterm or the journal club?
No lab on Tuesday. So you can use Tuesday morning lab time to either read the paper and write up your review, or you can do it some other time and use that morning for midterm, whatever you want.
Okay.
Can we get like extra credit or something if we do all of the journal clubs?
Yeah, I would strongly consider that. You know, if you want to do a write up for all of them, or if you're very active and you participate in the discussions for all of them, I'd be very
That's awesome. Cool.
Okay, so I'm going to send out these groupings later on, so that you have an idea which journal clubs It's just broken into Tuesday and Thursday. And the journal clubs will be in the afternoon. Okay.
Okay. Yeah, and so then you'll grade our journal clubs from yours, because I wasn't sure exactly what you were looking for, so I don't know.
I'm gonna, these first few critiques, I'm going to be pretty lenient, because I don't expect you guys to know exactly what I'm looking for. But then hopefully with that feedback that you get when I do get around to grading these things, that will help guide your future critiques.
Okay. It's a critique. For some reason, I thought it was just like a summary.
No, it's a summary and a critique. So you want to summarize the major conclusions of the paper, but I'm hoping that you also, if all the experiments were designed perfectly in your opinion, then you can say that. But if you were like, well, I don't know if I agree with this interpretation, right? Or I think that was a stretch, or I think that this experiment would have been better. If you're able to do that, that's what I'm looking for, those things in there. And then also what can be done next with the results of this paper, right? So I presented the paper on the compounds that were proposed to target SARS-CoV-2. And what would be the next steps? Well, to actually show that they kill virus, right? Or that they compete with that binding site for the virus, so they can't replicate. So that kind of stuff.
Okay.
That way, it's not just you simply, looking at the abstract and just copying it. I want to see that you're critically thinking about these papers. All right. Where were we? We finished.
Just getting into
6, right? Okay. Looks like we have 2 more problems, and then we're done. So let's go back and to sharing the screen. Okay, so we have this reaction taking place, and they're monitoring the concentration over time, okay? And this is the data from that. They want you to plot the data and determine whether it's first, second, or 0 order, write the rate law, write the integrated rate law, and then find the rate constant, okay?
Should we attach an Excel chart to this, or?
Yeah, please.
Okay.
So I plotted it here. Here's my time. And then in column B, wait, can you see my screen? Can you see this? Okay. So
Yes.
column B is just the concentration. So that would essentially be 0 order. Here's the natural log of concentration, first order. And then here's 1 over the concentration, so second order. And if you look at these plots, they all look pretty darn good, right? So that's challenging when trying to figure out, well, which order is it? And so for that, we can go and look at the R squared. So for 0 order, it's 0.995. For first order, it's 1, which you can't really, 1 is right on the money. And then 0.995 also for second order. So with that in mind, since this R squared is the best, we're going to say that it's a first order reaction. Okay. And the slope is a negative 5.01 times 10 to the negative. I'm going to write that down. Slope equals negative 5.01 times 10 to the negative 3. Yeah. Okay. Okay. So what do they want? They want us to plot the data. We did that. Determine the order of the reaction. We determined it was first order. So write the rate law, right? What do we say that is? Rate equals K times concentration of the molecule in the equation, right? And it's a first order, so to the first power, or we can just leave it with nothing. That is the rate law. What is the integrated rate law? Well, if it's first order, we use that integrated rate law for first order reactions. So the natural log equals a negative kt plus the natural log. Here. That is our integrated rate law. And finally, what's the rate constant? Or K. Now this is first order, so slope is equal to negative K. Right? So what is slope? It's a negative 5.01 times 10 to the negative 3. So a negative 5.01 times 10 to the negative 3 is a positive 5.01 times 10 to the negative 3. And that would be our K. And that makes sense because K should be positive, right?
I have a question.
Yeah.
Do you mind if I share my screen real quick?
No.
I don't know if it. So this one just below it, that's a natural log of A subscript T over A0 is also appropriate, or you have to do the one on top?
Oh, no, they should both work.
Cool.
Yeah. Because the natural log of something over something is the same as the natural log of something minus the natural log of that thing that it's over. Does that make sense? So it's just rearranging that equation. Yeah. So if you wrote that, that would be fine too. Okay. All right.
Sorry, the rate constant. So, is it just positive 5.01 times 10 to the negative 3?
Yes.
Okay.
Because the slope in a first order reaction, the slope is equal to a negative rate constant. And since the slope is negative, a negative negative is a positive. And it should be positive. So.
And then are the units seconds to the negative 1?
Units would be
Molarity per second, right? Or
we have our concentration, and then we have our seconds.
For the slope, so it would be molarity per seconds.
Mm-hmm. Yeah.
I thought it was just seconds to the negative 1.
That's what I thought.
I think it says that on that screen I just shared in your review slide deck.
Let's see. So I guess if you first order is seconds, okay. I guess because what you end up doing, yeah. So what you end up doing is you divide. If you want to get K by itself, and you take this, you have to divide. You have to divide this by this, right? And so, and the unit is molarity. So that would cancel out the molarity. But with a zero order, it's subtracting. No, because this is subtracting 2. Wow. I don't know. I have to think about that. I think
Isn't
about,
it just always first order reactions units for
yes,
K or second to the negative
yeah,
one?
it must be, but I'm trying to figure out why it's different between the. So if you share your screen again, if for zero order, it's molarity times or molarity per second, and so I'm just trying to look at that and see why it's canceling in a first order. But it must just be the way these equations are set up. To get K by itself, you're going to cancel out that the molarity for a first order, where it doesn't cancel out in a zero. And then on the second order, you're dividing by it. And that's why it's m to the negative 1. Yeah.
Carl,
Yeah.
just to clarify, you want us to send you you want a graph with number 7 attached to it?
Yeah.
You want us to do an Excel for it? Just to definitely clarify. Okay.
Yeah. Yeah.
Thank you.
And you want us to also, do we have to plot the natural log of NO2 and 1 over NO2, or wait?
That helps us decide what order it is, right?
Oh, okay.
So part A of that problem is plot the data to determine the order. And so to do that, you'd have to plot just the concentration and the natural log of concentration and then 1 over concentration and see what has the best fit for your trend line.
Okay. Wait.
And that will tell you what.
Okay. All right.
Yeah.
All right.
All right. Anything else, guys, about that? Okay. So for the last problem, it's asking for activation energy and frequency factor. So EA and A, right? They give us a few data points and we have to figure it out, right? Now, this isn't enough to plot, but we don't need to plot it to get the answer. We can just take these temperatures and these rate constants and arrange them in the Arrhenius equation to solve for activation energy. All right. So what do we know? We are given 2 temperatures and 2 K values. So T1 we can say is 900 K, and K1 is 2.14 times 10 to the negative 3. T2 is 1000 K, and K2 is 6.14 times 10 to the negative 2. Okay. Now, per the Arrhenius equation, and using it like a 2-plot derivation of that, we can say that the natural log of K2 over K1 is equal to activation energy over R times 1 over T1 minus 1 over T2. Okay. And so we just plug in. We have everything except for EA in this case, right? So to do that, let's see. We have T2 being, I'm sorry, K2 being 6.14 times 10 to the negative 2, and K1 being 2.14 times 10 to the negative 3, and R is 8.314 with a joules per mole K. Sorry if that's kind of sloppy. 8.314. T1 is going to be 900. And T2 is 1,000. Okay. And so if you, again, arrange everything to get EA by itself, so you multiply both sides, you take the log of the natural log of this, you multiply each side by 8.314, you take 1 over 900 minus 1 over 1,000, you get a number, and you divide each side by that, you should get EA by itself. And what I got was 2.52 times 10 to the 5th joules per mole equals EA. Okay, cool, good. So again, set this up. If you're getting a different answer, try it again. You know, order of operations applies, so you got to just make sure you're doing everything in the correct order, and it should work out to this. That is our EA. Now, how do we find the frequency factor? Well, we use a different equation. I'm going to erase this now. And this lecture, or I don't know, this review is being recorded right now, and I'll post it to a YouTube after this, so you guys can review it if you need to, if you missed something, if I erased too quickly. But we have a natural log of K equals a negative activation energy over R times 1 over T times, or plus the natural log of A. Okay, that's what we're trying to solve for, that A. We've got everything else we need now, okay? And we can just pick some value. So let's just pick T1, right? For instance, we could say that the natural log of so the natural log of 2.14 times 10 to negative 3 equals a negative 2.52 times 10 to the 5th over 8.314 times 1 over 900 plus the natural log of A. And I'm sorry I didn't put any of my units up here. This would be joules per mole Kelvin. This would be Kelvin, and so forth. But this would be this would be S to the negative 1. It's just kind of hard with limited whiteboard. So if you rearrange this to solve for the log of that, of A, it should come out to 27.53 equals natural log of A. And another way of writing that is E to the 27.53 power equals A, right? To get rid of the natural log. And if you do that, it's 9.04 times 10 to the 11. Okay.
I was struggling with that frequency factor. Thank you.
You're welcome. You're welcome. I will, like I said, I got to scan the key. I got to finish the key, scan it, and then I'll post it up there so you can check your answers if I went quickly over something, you missed it, or you can look at this recording. The midterm is now posted, and I'll post the groups for Journal Club so you know if you're responsible for Tuesday or Thursday. I now have a little partner here. One of my boys just put a lizard on my shoulder. And that's what I got for you now. Okay. Wow, and it's 2:50 right on the dot. Perfect.
Do you mind
Elke,
if I ask you a quick question about the midterm?
what's that?
I'm sorry, go ahead.
I was just gonna say, Elke, if you're still unclear about Journal Club and stuff like that, shoot me an email. I'm happy to explain further. The first couple Journal Clubs, we're just gonna try and get familiar with the process. It's an experiment, as the weeks go by, which there's really just 5 weeks left, I guess. You'll get the ball will roll. You'll get a better feel for it.
Okay. Yeah, I think for yours I just wrote a summary, so I'll change it up this time.
Okay.
I ask.
Okay. Anything else?
Wait, so you're posting this on YouTube? You're not posting it on Canvas?
No. Well, I post a link on Canvas.
Oh, okay.
I was trying to upload these videos to Canvas, and it wasn't working. It was taking all morning, and nothing was happening. So it's much quicker to post it to a YouTube channel, and then just embed the link into the folder. So this is week 6. So there'll be a folder in week 6 that you can look at that will have the link to YouTube that will be this recording.
Okay, awesome.
Okay. Good luck with the midterm. Again, I've kind of put the guidelines up there at the beginning, so you can feel free to chat with each other, your colleagues. You can't just simply copy someone else's problem, but you guys can work on these problems together. You can consult your notes and textbooks. You can look up things that are in the same concept. I don't want you to look up these problems exactly as they are, or I know that there are certain forums you can post answers to and say, hey, does anybody know how to do this? And again, you might get the wrong answer if you do that. So don't try that. Really work on this to the best of your ability, and just know that when I'm grading this, I just want to see that you're going through these motions more so than anything. Okay. So do your best work that you can do, with or without your colleagues, but try to keep it to that at that point. Okay. And you should do just fine. And if there's anything that doesn't make any sense or typos or something, feel free to shoot me an email. Okay. Alrighty. Well, that's all I got. So unless you have anything else, have a great weekend.
Thanks, Carl. You too.
Okay.
Thank you. That was helpful.
Great.
Carl, off topic. Did your one of your sons take the lizard, like make it kiss you and then run away?
Yeah. I'm back now.
I saw that. That was really funny.
You want to show him your lizard? Oh, no, he's being shy now. Oh, no, here it comes. There it is. There it goes.
Oh, nice. What a cool lizard.
Look at that. I'm going to watch your lizard. It's a crocodile is, it's in the lizard
Kind of.
family. So
Yeah. Thank you, Carl. That was super helpful. Yeah.
okay, so midterm problems are, kind of, some of them are pretty similar, plug and chug, just different values. Some of them are slightly different, but it should all be stuff that that we've covered for the most part, and so hopefully it goes well.
Okay.
And I did get your email. I got your email with your resume and stuff. So
Okay, cool. And then also, for Science Club, you sent out an email. Did I respond to everyone or did I respond to just you?
Oh, I'll have to check because I got your email.
Yeah.
But
I was like, well, because I also misspelled something. So I was like, if that went to just Carl, that's awesome.
yeah, I can check really quickly and see. Where is that? Ah, okay. Let's see. Oops. Um, yes. Yeah, I think you just sent it to me.
Yeah, because it said just to you. So I don't know. Maybe I need to like play with that and see like responding because I don't think I'm very good at chain emails at this point in time.
Just take the email that I sent
Mhm.
and reply all, and just copy that email that you just sent me,
Okay. With
and
the
that should do it.
spelling
Yeah.
correction, no.
Yeah.
Okay, perfect. All right. Thank you, Carl.
Okay, you're welcome.
And then we're doing journal club at 1:00 on Tuesdays.
Yes. So you are, if it's okay, I put you in the Tuesday group because that's when you and Elke are presenting. And so I know that you have a conflict, but I thought that was maybe in the morning.
Yeah. So and also it's not all the time. It's like random dates that I have the Zoom meeting with Tim.
So what we discussed this morning and hatched out for our plan is that we're not going to do any more labsters. You'll still do some labsters if you need to for your proposal. But we probably won't do many more labs. We'll use the lab time to work on whatever you want, whether it's homework or review a lecture or to read the paper and critique, brush up on it. So if you don't have a conflict, then you can use that time to work on the paper. And then in the afternoon during lecture time, that's when we'll discuss it.
Okay. So you don't have any more labs then for the rest of the quarter? It's just journal clubs?
I might. So there's this one bioinformatics lab that I wanted. It's not a labster lab, but it's just you go to this database and you have to find different sequences and design some primers for PCR and stuff. So I haven't thrown that out yet, but I'm going to throw out the labsters because it's kind of hit or miss, and I feel like for some people it's some people think it's terrible and some people think it's okay. No one's really like saying, yes, this is great. So I would rather focus on journal club and have you guys, figure that out. Then do these labsters that are just kind of busy work.
Okay, and then can I do the critique like a couple days early and send it to you and have you kind
Sure.
of tell me if I'm doing it in the manner that you want me to?
Yeah, absolutely. As we get into this, I'm happy to give you guys feedback on how they're going. I'm not going to be overly critical of your critiques at the beginning because I want you to kind of get an idea of what this is all about. But yes, that'd be great to send it my way and I can look at it and say, yeah, great. Or maybe think about this or that.
Okay, for sure. And then I had another question for you, but I can't think right now. Cody, do you have something to say? Just hanging out.
Cody, was there
Yeah, I
something?
was curious about the first question on the midterm. Yeah, I was trying to wrap my head around the full chemical equation. I know we're dealing with copper and 2 nitrates attached to it. And then we're also dealing with ammonium or ammonia. And I'm thinking that those are both reactants, and I'm trying to figure out what the products are going to be, but I'm kind of struggling to wrap my head around what that full chemical equation would be. Is that something you want me to try to figure out on my own, or?
Yeah, I mean, this is early in the game, so I would recommend that you try to just give it your best shot for now. That said, I'm happy with you consulting references to help you, because that will help you with that part. But it's not like you can just look up the answer online. So I'm not opposed to you guys doing that. If
Yeah, I
that,
kind of assumed nitrate's going to bond with the ammonium or the ammonia so that we have copper ions. But
Thank you,
yeah, I
Carl.
mean, I'd take some time to look around and do some research, but I'm not sure.
if you if that question comes up, just shoot me an email.
Okay, thank you so much.
Cool.
I'll see you later. Sorry to
Thanks.
interrupt.
So think of the so the solution is copper 2 nitrate. And so you have the ammonia. After the solution reaches equilibrium, how many grams of copper 2 remain? So you're trying to just figure out what the equation would be, right? At this point?
Yeah, I feel like the nitrates have to bond with the ammonia in order to free up the copper, but the ammonia doesn't have any kind of a charge on it, so I don't know why it would bond to the nitrates unless there was a hydrogen or something in there.
So think about it this way. They give us a constant. So I'm just trying to think of how to say this. I would plan on the copper. So the copper nitrate is just a kind of a delivery system for the copper. Okay. So what you end up having is copper ions and ammonia coming together to form copper and ammonia. That makes sense?
And I assume there's going to be excess copper ions because there's not ammonia for all the copper to.
Yes.
Okay. That makes sense. I appreciate it, man. I'm not trying to pry information out of you don't want to get out. I'm just like, how do I get started with this?
I didn't think that was the case, Cody. I my style. I don't like you to be lost, but I also like to nudge you. That was kind of a big nudge, but like, don't worry about the nitrate. So when you're doing your equation and you want to form your ice table, concentrate on copper and ammonia and how they come together. Don't worry about the nitrate.
That's a big help, man. Thank you. I appreciate you reviewing the midterm review too. I was definitely looking forward to that.
Okay. Yeah.
With the home learning stuff, to be honest with you, man.
Yeah, it's hard. It's challenging, and this format where it's just recorded lectures is good in some ways, but then you don't get this kind of interaction, this feedback this way, and I missed this, so I'm glad it was helpful for you.
Yeah, I appreciate it, man. Very, very clear and concise. Thank you.
Great. And my 2-year-old Theo slept the whole time, so worked out well.
Hey, it all worked out.
Yeah. All right, well, hang in there. It looks like I have you you are in Tuesday. Yeah. So
yeah.
So just keep that in mind for Journal Club. Try to balance things as best you can, and we'll see you next Tuesday.
I was pretty impressed with I think it was Jonina who shared her screen with her summary or whatever. It looked like very, very well done. I'm like, man, I got to step it up a notch. That's way better than that.
Yeah, I know that that they've taken a lot of classes, and they're basically taking this class to kind of retake. They've already had chemistry. They're just trying to retake this class, and so they've been through a lot of different courses. And I think that those instructors have probably done things that are maybe kind of similar. So it's not completely unfamiliar territory. I don't think that the instructors at LTCC are doing this kind of stuff that I know about. Like, I don't know of any journal clubs or research proposals that students are made to do. They do this research project, but it's really kind of like research proposal light, So I think that they're more experienced with this, and so But that's what I'm looking for. I mean, like when she showed me that and she was like, well, what about this? And I'm like, wow, you're really going into the details. Yeah, I mean, if you
setting the bar, man.
Yeah,
it's gonna be the top one right there.
Yep. And it's hard for me to sometimes realize, because I've done this stuff so much that I take for granted how novel and new it is to the students, and how I'm thinking, okay, well, I just say they do this and then they'll get it. But I need to work on my explanations and my expectations a little bit better. So that's on me. But
no, you're good, man.
At any time,
just
shoot me your outline. Your outline is going to be due in a few weeks, so shoot it my way. And if you want any critique or feedback before then, I'm happy to give it to you.
I appreciate it. Thanks. I'll try to get that done.
Okay, sounds good, Cody.
All right, man. Enjoy your weekend. We'll see you Tuesday.
All right, sounds good. Take care.
All right.
Bye. All right. Yes.